Go in the fish tank here for some high-level deep dive talking about propulsion with you. So I want to hide behind the glass in case there's anything goes off that is very dangerous. But today we're going to talk a little about where the thrust equation came for rocket propulsion. You'll see in your book some equations, different equations for rocket propulsion, but there's a basic thrust equation, and we're just going to take a little deep dive and try to demystify where that thrust equation came from. So when we start out, we often talk about just drawing a picture of a rocket motor in a very simplified manner. It just looks like a big can with a hole in one end. That's our definition of rocket motor for right now. And if you remember the nightmare of fluid mechanics, we remember that we define control volumes in order to kind of keep track of momentum, where momentum and forces are on the outside of that shoebox. It's the round side of this device. So the trick is you have to figure out what's coming through the device and what's touching the device to try to stop it or make it move. So in order to make this rocket motor not move, we're going to put a big force on the front of it so it stays on the board for us. And what else is happening that's coming through on the inside or outside of this control volume? Well, we're going to have some mass flow rate coming out of the back of it. We'll just assume it's coming out straight, and it's going to be coming out at a certain velocity that we'll call the velocity of the exit. So all around the outside of this control volume, there's also pressure forces. The pressure force on the bottom is the same as the top if you think of it as a shoebox, and the pressure force is acting on the front of the rocket. But there'll be a different pressure force acting around the area of this nozzle because we'll discover when we examine more closely that the pressure of the exit plane of the nozzle can be different than the pressure at the ambient. So outside pressure the rocket doesn't know the ambient pressure is there because it's coming out supersonic, so the flows can't go upstream on you. So pressure ambient's the outside. So we have two things going on here. We have pressures on the outside of this box, and we have a bunch of momentum coming through the back side of it. So I'll give you the bottom line up front. The equation in the book for the thrust of the rocket motor is just that mass flow rate coming out of the back times the velocity of the exit plus the pressure of that exit minus the pressure of ambient times the area of the exit. So we have two different forces that are acting, or two different concepts that are making the rocket go. The first one is called the momentum thrust. This is the thrust that's due to throwing stuff out the back. So if I were standing on a skateboard here and I had some big rocks and a very slippery skateboard and I started throwing rocks this way, I would start going back this way because there's a force on my hand when I push it off that's equal and opposite. If you think of it another way, the center of mass of everything that started stays in the same place. So if I throw a lot of mass this way, since the center of mass has to stay the same, I go the other way by a proportional amount. So that's all rocketry really is throwing rocks that way so you can go that way. That's the bulk. This momentum thrust is the big term. But there's also a smaller term. When they first thought about rockets, they didn't know if they would work in space because they didn't have any air to push on, but momentum doesn't require that. There's also another term here. This is called the pressure thrust here. And the pressure thrust has to do with the imbalance of the pressure on the back side of the nozzle and the pressure on the front side of the nozzle. So if I looked at the end of this control volume here, I would see a circle where the nozzle is, okay? And that circle is not at ambient pressure, it's at the exit pressure. So this is all at PE right here. And on the front side, it's all at ambient pressure. So if you've ever gone to the bank or the pharmacy, especially during COVID, they send that little cylinder out there, right? And how does that work? Well, you put it down in there and all of a sudden it goes and your stuff goes off, and then you say yes, thank you, and it comes back with your receipt and a sucker, and all the money goes in the bank. So it's the same thing with a rocket. You have this pressure force here, and actually this pressure is usually lower, so it's actually trying to push the rocket and reduce the thrust a little bit. So the pressure thrust is the minor part of it, but it still comes into play. So the momentum thrust depends on how much mass you're throwing out and how fast you want it to go. So that's why you want to have a lot of mass in your rocket motor to push that out. and you want to make it go very fast. Again, if you're thinking in terms of throwing the rocks as far as you can, the faster that velocity is, the farther away those rocks are going to get from you in a certain amount of time, so the further you can go into space or wherever you're trying to go. So high velocity is good, mass flow rate is good. Then these are minor terms here, but what changes when you're flying a rocket, especially if you're going up into space? Well, the ambient pressure is probably going to go down, right? So if you start at 14.7 and you go all the way to space, this is going to go to 0. So all of those things being equal, as this one starts to go down, then your thrust is going to go up with altitude. So if you just sort of did a rocket motor and you said, this is my altitude and this is my thrust, if you started at sea level and went all the way to vacuum, you would come up and reach a higher thrust because of this last term here if everything else was the same. Now there is a point in the middle of this thing here where the exit pressure is equal to the ambient pressure. It could be somewhere in the flight here. And the point, if this was where the exit pressure was equal to the ambient pressure, that's a P there. At that point where P x equals P ambient, that's called optimum or ideal thrust. Now let's learn to write a little better. So, so when we're at that optimum thrust, this pressure on the front cylinder here is exactly the same as the pressure on the nozzle, so there's nothing's going anywhere. So it's the same idea of sucking soda out of a bottle. You lower the pressure in your mouth and it pushes things out, but if you could make it just all not go anywhere, the pressures would be balanced, all the forces would be balanced. So that's the overall concept of the thrust equation in a big picture. If you go back to fluid mechanics, there's a very general equation that you can use to derive this, and you probably classically see it when they do the how much force is there on a hose going around a corner type of thing, where you have momentum going in different directions and you're trying to turn flows and go around. But this proves a couple of things. It proves that rockets can operate in space because even if the pressure terms are very small, but this momentum thrust is always acting, so you can always throw stuff out of the back of your rocket engine to generate thrust and go in the other direction. And the pressure thrust is important in that it'll make your thrust vary with time as you go up, so that's important in computing your trajectory. And it also helps you design the right kind of nozzle, because you'll see nozzles with much larger exit areas in space because you don't have this penalty for the pressure at the exit. All right, so this is just a little demonstration of a quick deep dive. I would come back and do more if I was teaching the other class to go back to the set of equations that we used to get there, but it's conservation of momentum for a control volume. It's a very general equation from your fluid dynamics book. But this is just a short clip in order to help you remember some of the things that you had in previous classes. So this is our deep dive from UAH, number 001. This is our prototype, first time through, and we'll see if how you like it and if this might help you engage with your instructional material a little bit better, and especially when we're doing equations. So that's all for today.